In this video, you are going to take a look at how to solve a question given under mathematical induction. For this question, I have selected a statement with series notation. We have to show this statement is true for any positive integer using mathematical induction. Before starting the question, let's see what is the meaning of this series notation. Sigma r equals 1 to n r. Meaning of this is we have a series of numbers which is represented by this common term r starting from 1 to n. So it can be 1, 2, 3 up to n. This series satisfies the common term r. Let's say we have a series. First term is 1 into 2, 1 over 1 into 2. Second term 1 over 2 into 3. Thirdly 1 over 3 into 4. So this is a number series. First term in the denominator is 1. First term in the denominator for this second term is 2. This is 3. So what is the pattern? 1, 2, 3. It increases 1 by 1. Then the second term starting from 2 becomes 3, 4. So it increases 1 by 1, but starting value is 2. Numerator is 1. By considering those, we can write a common term for this series. It is 1 over r into r plus 1. This is actually a part from series lesson. When I increase or when I substitute values for r, we can obtain these terms. When I substitute n equals 1, this becomes 1 over 1 into 2. R becomes, this should be r. When r becomes 1, this becomes 1. When r is 1, 1 plus 1 becomes 2. Then when r equals 2, our fraction becomes 1 over 2 into 3. Substitute 2 here. 2 plus 1, 3. Therefore, the common term for this series is 1 over r into r plus 1. Then what is this sigma? Sigma r equals 1 to n means we have to continue our series with this common term starting from 1 to n. So we have n terms of this particular series whose common term is this. So it is a series. So intentionally I took the same common term which we have in this particular question. Let's start with this mathematical induction question. In previous video, I taught you how to solve a question given under mathematical induction using 3 steps. If you have not watched that video, I recommend you to watch my introduction video on mathematical induction before watching this. So let's start. First step is to show the statement is true when n equals 1. So when n equals 1, the statement becomes sigma r equals 1 to 1 because n becomes 1. Common term is 1 over r into r plus 1 equals, for n I have to substitute 1. Then this is 1 plus 1. So we can see this part sigma r equals 1 to 1 means we have to consider only the first term, starting from 1 finishing from 1, so we have only one term. Then r is just 1, therefore we can see our left hand side becomes 1 over, here we have to substitute 1 inside the bracket. For r also we are going to substitute 1, so here we have 1 into 1 plus 2, it is 2. 1 plus 1 is 2, so answer for left hand side is half. Then what is our right hand side? It is just 1 over 1 plus 1, it is also half. Therefore LHS equals to RHS. Therefore statement is true when n equals 1. So you have done the first step. Second step is the assumption. We are going to assume the statement is true when n equals any positive integer. I take it as p. Statement is true when n equals p, where p is a positive integer. So what is the result? Sigma r equals 1 to p. I have to replace n by p. This becomes 1 over r into r plus 1, the common factor, same thing. This is p over p plus 1. Instead of n in the statement, I have to substitute p. So this is the assumption. Then third step is to show the statement is true when n equals p plus 1 using this assumption. For that I have to consider n equals p plus 1. Then what will happen to our notation, sigma notation? This moves to p plus 1. Earlier we had p up to p. Now we have p plus 1. What is the difference? We have a series. Earlier that series starting from 1 moved up to p. Now starting from 1 it goes up to p plus 1. That means one term more than this assumption. One term more than this earlier assumption. What is that term? What is that additional term? It is p plus 1th term. I repeat, this went up to p. This goes up to p plus 1. That means we have one additional term, that is p plus 1. So this is the common term of our series. 1 over r into r plus 1. So this goes p plus 1. That means this term we have to replace our r values by p plus 1 to obtain p plus 1th term. This is p plus 1. This becomes p plus 2. Now this is equivalent to sigma r equals 1 to p 1 over r plus 1 plus n plus 1th term. So I separately wrote the idea of this left hand side. Sigma r equals 1 to p plus 1 can be written as sigma r equals 1 to p plus the last term, p plus 1th term. This is equivalent to p over p plus 1 from our assumption, from this one. This is p plus 1, so p plus 1 term is 1 over p plus 1 into p plus 2. Now we have to simplify this and get the new expression for this when n becomes p plus 1. So first, it's better if you can write the result and target that result for this simplification. So what is the result we have to get? We have to substitute p plus 1 for this n. Then this becomes, our right hand side becomes, I will write that here, p plus 1 over this n becomes p plus 1 plus 1. Then we have p plus 1 in numerator and p plus 2 in denominator. So this is what I want after simplifying this. For these two, I can take the common denominator, that is p plus 1 into p plus 2. Then this numerator p is multiplied by p plus 2. This is 1. Now remove brackets. We have p square plus 2p plus 1 divided by p plus 1 p plus 2. Now this quadratic expression of p can be written as p plus 1 whole thin square. Expand p plus 1 whole thin square. We have p square plus 2p plus 1. So instead of p square plus 2p plus 1, I can write p plus 1 whole thin square. So denominator is p plus 1, p plus 2. I can cancel 1. Then the answer when sigma r equals 1 to p plus 1 over 1 over r into r plus 1 is p plus 1 over p plus 2. So this is the correct result we want. Now we can finish this question by writing the final statement. Therefore, our statement is true when n equals p plus 1, as it is true when n equals p. So we could get this result using the assumption. Therefore, the statement is true for n equals p plus 1 as it was true for n equals p. Therefore, from principles of mathematical induction, for all positive integers, the statement is true.